Okay, good afternoon and welcome to the Winter Spring Cryo-EM course. Our guest lecturer today is Reza Khayat. He's from the Center for Discovery and Innovation from CUNY. He has a long history with Cryo-EM and he is one of the rare people who has used Leginon, and that's going to be a topic of discussion that we'll have a little bit later in the course when we go over some of our pre-processing. So welcome, Reza. How are you doing?
I'm well, Ed. How are you?
Oh, great. So I'm going to introduce you to the class for a little bit more. How did you get into Cryo-EM?
So I got into Cryo-EM. I was finishing up my graduate work at Columbia, and I went to some sort of a structural biology seminar series at City College. And over here, there was someone who was talking about EM, and the topic was future of structural biology. And they were talking about tomography, and they were essentially saying that they think that the future is a combination of electron microscopy and X-ray crystallography. So they sold me on that topic, and then I went to Jack Johnson's lab at Scripps Research Institute, who's one of the initial people who actually, crystallographers who actually believed in cryo-EM. And he was a huge proponent of cryo-EM, and he was one of the few people who's doing hybrid, who's fitting in high resolution crystal structures into cryo-EM maps. And cryo-EM maps at that point were around 25 angstrom. So I went to his lab to put the two together and look at larger complexes using electron microscopy. So that's what got me into the whole field.
Okay. Do you have a favorite microscope when you first got into EM, or just today, a microscope you'd like to use?
My favorite, yeah. So initially I started working on the F20. And this was, again, at Scripps Research Institute. It was one of the F20s that Bridget, so starting from the first day of my electron microscopy, I've been friends with Bridget and Clint. So I was initially put into one of their lab spaces. So they've been extremely kind, generous, and helpful towards me in my entire career. So it's been fantastic in that regard. And the first microscope I started working on was an F20. But then after that, my favorite microscope became the FEI Morgani. And that's a microscope we don't have anymore. But it's phenomenal to just put some sample on, start imaging and see the quality of your sample. And within 15 minutes, you know if you have good sample or garbage. And it's just phenomenal for negative stain. So that still remains to be my favorite microscope. After that is the 1230, because again, the JL 1230, because I like things, you got to look at a lot of samples. And you got to look at them in negative stain before you're ready to go into ice. And taking time and like putting it on, for example, on the T12, which is the next level of low end microscopes, that takes too much time. I like to go quick and just screen through a bunch of conditions to try to get something that stabilizes the complex. So that's my favorite microscope.
And the 1230 holder has a bit of mass and has a double O-ring system, so it's harder to crash to vacuum.
Yeah.
And it's more stable.
Yeah.
So
and when it crashes, it comes right back up.
Oh, that's a good thing about when you have a 120 kV microscope instead of these FEG microscopes.
Yeah.
In terms of the field of EM, you've been sort of there in the beginning before direct detectors were so mainstream. So for you, how has the field changed over these years?
Oh my goodness. So I came in the CCD era, right? And everybody collected images on the CCD with a few labs who were still collecting on film. And some of these labs were collecting negative stain on film. Nobody understood why. I still don't understand why, but that was their preference. The other groups that were collecting on film were to push the resolution. This was like Hangzhou, Hua Chu's lab, and students that came from his lab. So that was one thing. But when the direct electron detector hit, in the very beginning, it was promising, but we were still aware that there were still hurdles that needed to be overcome. But once those hurdles were overcome, it's just a jump in resolution. I imagine it would be something like maybe jump to 5 angstroms or 4 angstroms, looking at highly symmetrical entities like viruses. But I never imagined that we'd get to this day. I still looking at particles in ice, seeing them, coming from an X-ray crystallography background where you're seeing spots, you don't see proteins, and seeing proteins and actually getting maps of those proteins, to me is obscene. It's unrealistic. And it seems like there's something wrong with it, but it's happening. I mean, that's how unbelievable the whole thing to me is. And having seen it evolve, it's just, it's still like it's some sort of a weird dream, is how I would describe it.
You said you're coming from an X-ray background. Are there other fields that have come into cryo-EM that surprised you?
Yeah, you know what? We're getting neuroscientists coming in. You know, there's a lot of the Yifan Cheng paper that did the trip work essentially blew open an entirely new field. And back in the day when I started doing EM, you had to really know what you were doing, right? You could do some wishy-washy work here and still get its reconstructions or maps out. But nowadays, with the software having been essentially simplified, things automated, you're getting people that really didn't do much biochemistry in the past, but now, or they didn't do hardcore biochemistry, but now they're expressing their membrane proteins and they're getting structures out. And these are labs that used to that didn't even collaborate with structural biologists, that weren't even interested in structure. They would do, like, for example, just patch clamp work, right? And the functional studies and things like that. I mean, it was beautiful work, but they weren't really interested in structure. And then when this paper came out and they realized how readily available this technique is, and I really want to emphasize, because if you compare this to like NMR, who's been around a lot longer and who's received a lot more support, financial support from the NIH, when you look at the structural biology initiative, cryo-EM is just like, has had less support and is just providing a lot more support and a lot more less support and a lot more outcome, right? It's accessible to anybody. So seeing the neuroscientists come in here and get these high quality papers, that just shows you how many people have worked on this field, how mature this field has become in such a short period of time.
As we move and the field grows, what challenges do you see that are among us, and what do we have to tackle?
So I think there's better people who think about these things than I do. So I think heterogeneity is still a problem. Particularly, some of these questions have been, how do you deal with continuous heterogeneity? I think that needs to be dealt with. Obviously, tomography, there's a lot of work that can be done in that. Tomography, as of this point, there's still a lot of similarities to how data and tomography is being processed to how, for example, SPIDER in single particle analysis used to work, using, for example, correlation coefficients to find the optimal position rather than using something like maximum likelihood, or even looking at machine learning. So there's a lot of improvement to be done in that area. But the obvious ones are like expediting the process, looking at smaller particles, getting out heterogeneity, dealing with drifts, but drifts are being, or things like that. But again, like I said, there's people who do a much better job thinking about this stuff because they're more interested in the technique. I'm more interested in using the technique for answering science questions rather than improving the technique and breaking those boundaries.
Okay, so let's get into some questions. Are you ready?
Sure.
Okay, so for you, when did the resolution revolution begin? I don't like that term, but do you like that term, resolution revolution?
It's a catchy phrase. I don't, people can use whatever phrase. I don't have a big deal with, a big problem with it. For me, when it happened this is shortly after I started my faculty position at City College. That's when the paper started coming out. But I was there, again, I was at Scripps Research Institute, same building that Bridget and Clint were running the NRAM Institute in. And they were collaborating with individuals at UCSD who were developing the direct electron detector. And I was friends with the graduate student who was actually leading the entire process. So I didn't have any input into solving any problems, but I saw it coming along, and I saw all the hype, and I heard and I felt the buzz, the energy going around about this thing making some fantastic breakthroughs. Like I said, I imagine getting to 4 angstroms where we are right now. It's really unbelievable and surprising.
When you're processing data, how important is B factor for you? What metric do you use when you're starting to compare data sets, or when you're starting to do analysis to say, oh, am I improving?
So B factor, look, I've had reconstructions that had B factors of around like minus 120. and the reconstruction was reasonable, right? And I've had reconstructions that had a -120 and they were also they were garbage. I don't have any way of explaining this, but I can tell you that B factors are not really any sort of a metric you should use for validating your structure at the very least. What I would recommend is, does it make sense? For example, if you're talking about validation, um, if if you don't know what a structure looks like, if looking at high resolution may be confusing for some individuals, low pass filter it to 7 angstrom resolution. Do you see sausages? Sausages explain alpha helices. Do you see sheets? Do you see secondary structure elements in your structures? If you don't, and the FSC is telling you 2.9 angstrom, it's garbage. The FSC is not a way of getting at resolution or for validation, I'm sorry. FSC could be used for resolution. So for assessing, validating, I think it's a good old way, the same way you do in X-ray crystallography. Do you see secondary structure features? In X-ray crystallography, you look for helices, you look for strands. Same thing with EM. Now there's the so I don't use B factor for anything other than sharpening the image to get the features to pop out. Now, if you don't do temperature factor correction, you're not going to see the high resolution terms, meaning you're not going to see the side chains in that. However, one thing you should be aware of with B factors is that, for example, CryoSpark and Relion will give you one B factor, and this B factor can screw up your low resolution terms. Meaning, for example, if you have regions that are dynamic, a high B factor, an aggressive temperature factor refinement will essentially blur out these regions, or it'll just make it into dispartite density. So you should, whenever you have your reconstruction and whenever you see your side chains, move one step further and make a 5 angstrom map, make a 7 angstrom map, and then make a 25 angstrom map, and see if any additional densities pop out that is not present in your higher resolution map. And if it does, then your temperature factors are actually getting rid of very important features. And those important features, while you may not be able to model any atomic coordinates into it, they will tell you a lot about your biochemistry. Number one, that it's a dynamic region, right? And that could be a good story for you to tell. So go through and do that exercise. And I think there was another question about, I think in the same question, there was a question about R factors. So there is, in X-ray crystallography, a lot of microscopists point to this and say we need R factors, and R factor is the holy grail. And really, R factor in X-ray crystallography is BS, not wanting to say the full word. And what's really important is the R-free factor. You can have a structure with a really good R factor, but it's wrong, right? And what really saved the R factor was the R-free factor, where you put a particular, maybe 8% of the data aside, you don't refine against that, and that's what you use for calculating R factor again. So it's not just R factor, it's R-free. And what EM really could use from is the R-free. Now, having said that, if you look at any X-ray crystallography papers, you look at table 1, there's a bunch of things that go in there, right? You have your completeness, you have your multiplicity, unique reflections, total reflections, I over sigma, Wilson B factor, CC 1/2, which comes from Cryo-EM, your RMS Ds for your bonds and angles. So, and clash scores. In addition to this, there's a bunch of additional things that you don't see that you have tables for when you're indexing your data and you're integrating your data. So, and the point is that you have all of these factors because a single factor is not good enough. And I think looking for that single factor is not the right thing to do, because you're not going to find it. And you'll get young crystallographers arguing back and forth over which one is the right thing to use. And the older, more experienced ones will say, look, what's the story? What is your R? What is your R-free? What resolution are you at? And what are you trying to say? If you're at 3.5 angstroms and you're talking about protons, then you got the wrong story. You got to be at 1.2 angstroms if you want to talk about protons. If you're at 1.2 and you want to talk about the fold of a protein, what are you doing at 1.2, right? So it's I don't think there's a single number that validates a structure. What validates is, can you put amino acids in there? Is it chemically meaningful? If there's if you do functional studies on there, if you say, this is the active site, I'm going to mutate it, does it knock out your activity? Can you predict with that structure what the function, how you can change the function of the protein? And can you test that? And if you can't do that stuff, then you're just building a bunch of sticks into a density and it really doesn't mean anything. You need to be able to predict. And that's what structural biology does.
Can you talk a little bit more about algorithm development and how that has improved, and what developments in the future do you see will make the biggest impact?
So algorithm development, obviously, look, Legion, you said I'm one of the few users of Legion. That's absolutely shocking to me because Legion essentially blew open the doors for EM. It's one of the big things that made it accessible. Again, I was there when this was being developed. I didn't have anything to do with it rather than talk and have fun with the people who actually did the hard work. In that it made EM accessible to anyone 24 hours a day, right? Before that, you had people going in at 9 a.m., starting up the microscope, aligning till 1 o'clock, and then collecting data till 5 o'clock and say, that's it, I'm going home. What Legion did, which is software development, says, okay, everything is aligned. We're going to start collecting data, and we're going to collect 24 hours a day, right? And we're going to go for 2 days, at which point the microscope really need to have a cryo cycle. And this just changed the entire field, because then reconstruction after reconstruction were coming out from and high quality reconstructions, right? So this was the first major step in making this thing accessible to a larger community. Now, having said that, if you go back a couple of years, obviously Spider, some of these earlier programs were seminal in making this entire process. Without Spider, you really wouldn't EM field would be different. So I don't want to overlook that. But having said that, I think software development, without it, you're going to look at some of the other fields. I don't want to mention these names again, but you have fields that are in structural biology that are extremely difficult, and because the software development is just not there. The scientists say that, oh, this is a very hard technique, but it's compared to it's the software development is not there. If you make good software, anybody can walk in and get structures out. And this is what the vision has been for some labs. It's just to make this idiot proof and to put your time in doing science than doing technical aspects of it. So and then motion correction, there's a couple of different variants of this that has been enormous. Reliant has been a huge step forward because it brought in maximum likelihood. It made 3D classification routine. It started pushing resolution. You have the multi-body in there. You have CTF refinement in there. All of these things add little bit at a time, and they're really what's making the high resolution structures possible. And then CryoSpark is also making huge advances. It's making the data processing just trivial. Trivial in the sense that it's easier for people to use. You don't need to know as much. It's also so amazingly fast that you can try so many different ideas on there. It's got its advantages and disadvantages, but like for example, if you look at CryoSpark Live, as the data is coming off of the microscope, this thing's improving the reconstruction, and it's going to tell you, hey, buddy, you've got anisotropy in your data. You got to tilt the stage, collect more data, improve your reconstruction in your home. And you can, by looking at these things, you can say, okay, we collected enough data, let's change the grade. So the next stage will be making software that can make the microscope intelligently collect data and say, okay, we've collected enough, stop collecting, put in another grade. So software development is a huge requirement for improving EM and making it more accessible to the general population, to the general scientific population.
A lot of samples people are working with are getting more and more dynamic. How would you deal with a data set that not only has different conformations, but might have a continuum of conformations?
Yeah, so this is a good question. So there's two ways of dealing with it. There is trying to collect tons and tons and tons of data and use some software that can do it. So CryoDragon, I haven't worked with this software, but this is supposed to deal with the continuum of data. And WARP is supposed to be really good at combining data that are heterogeneous and pushing the resolution. Again, I haven't worked with WARP at all. So And then CryoSpark, you can use 3D variability, and even with Relion, you could use multibody to look at smaller components. But with CryoSpark, as I understand it, 25 kilodalton is the minimum for where this works. And I think you need something a little bit larger for Relion to work. So my suggestion would be to use some sort of biochemistry. I know if you use antibodies, if you use fabs can lock things down and you can get at structures this way. But your interest may be looking at different conformational states because that's where the biochemistry is at. In that regard, I would say maybe look at small molecules. If you're looking at receptors, look at antagonists. And because with this kind of stuff, you're going to get both the structure and you're going to get the biology out of it rather than getting just the structure out. So while there are software that are being developed or have been developed to try to address this, sometimes going back to biochemistry and figuring out, again, this is where that favorite microscope comes in, right? The negative stain microscope is to lock it down, say, sometimes if you're using, for example, proteins that are involved in metabolism, you could try its substrates that bind to it, its cofactors, and see if you can stabilize it. And this will give you information in the biochemistry of what's going on. And I think that's far more interesting than just getting at a higher resolution.
Okay. Let's go to some more specific processing questions. For example, if we have a particle of interest, how do you choose the right box size, not only to excise, but also when you want to bin?
Okay, so the right box size is one of the harder questions. So, you know, if you look around, you see numbers like 1.5 to 2x. Back in the day, I was told 3x the size, the largest diameter of your particle. And this all comes really from signal delocalization. And it has to do with particles that are outside, really the field of view of not just of your particle, but field of view of the detector that are contributing to signal inside where your particle is. And you want to pick the box size big enough where you're getting sufficient data coming in from that you need to align with, but you also don't want to pick it large enough. So the box size ultimately, in my experience, really hasn't made a significance in terms of going from no structure to a structure, right? The box size has been important in improving the resolution, but it's never been like, oh, I'm using 2 times the size of my particle and I'm getting garbage out. Maybe if I used 4 times the size of my particle, now it's going to start working all of a sudden. That's never been the case. It's always been, if it's working, then, well, I mean, obviously, if your box size is too small and you're cutting into your particle, then that's just not going to work, right? I'm saying starting from something that's reasonable. In my experience, it has never worked, but the numbers have been 1.5 to 3 times the particle. There are equations out there that, for example, say at 300 kV, you want 400 times Z divided by D, where Z is the defocus in microns, and D is the highest resolution you want, okay? So you'll get equations out there, and there's even more sophisticated equations than that. But these equations tend to be more important for the smaller particles. And you know, some individual, and there's good discussions on CryoSpark. There's papers in bioarchives. I can paste these things into the chat. Let me find these. Actually, more chat. So let me paste some of these in here. So here's a paper I would recommend reading by Bob Glazer. Here is a program by Takanori Nakane that's responsible from Shore's Lab, MRC, LMB. And here's a good discussion on CryoSpark that will put you guys in the right direction. And there's been some concern that you shouldn't collect at too high of a defocus for small particles, like don't go anything smaller than 2 focus. But then Bob Glazer recently had a publication where he said that's not so much of a problem if you do the appropriate things. So so it's give or take, but I mean, it's if your particles, if you're getting if you're not getting reconstructions or if you're not getting good 2D class averages, I don't think fidgeting around with this kind of stuff is gonna help you. It's you got to get thinner ice, and you got to and maybe there's something wrong with the particles. Maybe they're just not amenable to cryo-EM, and not everything else. So that's essentially everything. Let's see what else was there. And that's about all the things I have about box sizes. Was there something else to the question I missed?
I was always heard 1.5 to 2 times the particle size. I think you
Yeah,
addressed that.
yeah,
And about SNR.
yeah. So again, the SNR thing is that if it's not working, I played around with this. If it's not working, it's just not going to work. You go back, make your ice thinner, make your ice thinner. And there's ways. Leginon does a beautiful job of measuring ice thickness. The old-fashioned way is to burn a really tiny hole into the ice, tilt the stage, measure that distance, and you know the angle, and from trigonometry you can figure out what the ice thickness is. But Leginon has built-in routines that can tell you the ice thickness nowadays.
Do you have any tips or tricks to working with small proteins?
Yeah, so CryoSpark, from what I've read, CryoSpark seems to be good with working with small proteins. And again, on the forum, it's got these weird variables that I just can't remember. I've got them in my notes, but if you go on there, there's in the discussion group, and you can play around with various factors that will improve getting the smaller particles to work. Now, one thing I can say about smaller particles is that if you generate, for example, 25 angstrom maps of a couple of different proteins of the same molecular weight, they'll all pretty much end up more or less looking the same. So having said that, your lower resolution terms are not that important in your alignment. And it's actually the higher resolution terms, sometimes better than 10 angstroms, that actually help you do the alignment. So when you're doing, for example, if you're getting good 2D class averages, but the 3D is not working, try putting more emphasis in the higher resolution terms, and try stepping away from the lower resolution terms. And that'll actually help you align on the helices and the beta sheets and getting some sort of an initial ab initio reconstruction out. And I would say try every piece of software you can get your hands on. Because sometimes one software just as an X-ray crystallography, some software works better than others. I can't come up with the reason why, but I've had this experience in my hands.
Do you have any recommendations for people starting out in processing and aren't familiar with all of the flags? Are there any reviews that would also be helpful?
There are reviews. First thing, do a tutorial. This is one of the beautiful things with EM. Every piece of software gives you a tutorial and says, this is what you need to do to get to high resolution. Now, that tutorial doesn't work for every structure that you're going to work on, but you know what the pipeline looks like, right? Do the tutorial. Don't do the tutorial with your data. Do the tutorial with the data that is recommended. You want to work on something where you know what the answer is. It's just like in math, when you took through in K through 12, you're not working on novel problems. You're working on a problem that's in a book. That's every other student that used that book worked on that problem. So don't go, oh, I'll just use this tutorial and work on my data. That's just naive. It's eager. You're really eager about starting a project, which is fantastic, but it's naive because you're going to do it. You don't know what you're doing, number one, and number two, you don't know if your data is going to work, right? You may be doing the tutorial right, but your data may just be garbage, but you don't know that. You've never done it before. So use the tutorial, and that's going to start telling you what some of the variables are. Get on the 3DEM mailing list, get on CCPEM, lots of knowledgeable people in there, answering questions quickly, get on all these discussion forums, but really know how to do the tutorial before you start asking questions. Because you don't want to ask a question where they're like, well, dude, just do the tutorial. The question that you're asking is covered in the tutorial. So that's my recommendation.
Could you talk a little bit more on the pros and cons of different software, for example, Reliant and CryoSpark and System?
Sure. So every software exists because it's a little bit different than the other software. Okay. Um, Relion and Cryosport, for example, at the most basic level, use GPUs. System, to my knowledge, does not. EMAN 2, to my knowledge, does not. Neither does Sparks does to a, or Spire does to a certain extent. So that's just at the very fundamental low level um, ideas. Other levels, for example, Relion has multi-body. Cryosport has this 3D variability that's not really like multi-body. You don't get that motion that you get with multi-body. I don't know of any such thing in System or any such thing in Spire. Um, Cryospark is really good with its ab initio. Reliant has gotten better with its ab initio. Spire and EMAN 2, they've gotten better with them. I haven't used them all that much. Um, ISAC that's present in Spire is supposed to be one of the best 2D classification algorithms out there. Um, so that's one difference between there. So every program has some advantage. I would not say pick this program and go with it because you need to be able to, the most important tool you can have as a structural biologist is the ability to use any software at any time, right? And anytime, I mean, if you need to be able to say, oh, there's a new piece of software out there, it has these capabilities, I have the ability to install software and to make it work. You don't, if you want to call yourself a structural biologist, you got to be able to do that. You can't run around and say, hey, buddy, install it, to ask your system administrator to do that for you. You got to be able to do that on yourself. So that's one of the important tools. And then the other tool is your ability to pick up software and use software at will. You read the instructions, you can read manuals, you can follow tutorials, and you can figure these things out on your own. And then you move forward. So I wouldn't say start with this program and then go to that program. Every program has its advantage. Cryospark is super easy to use, but the lack of a command line interface pisses me off, right? I love command line interface because that's what I grew up on. Reliant has a command line interface, and that regard is phenomenal, right? It's got a whole bunch of options I'm not familiar with, but I can write scripts for it. That's extremely powerful. Cryospark is extremely fast. So what I like to do is I like to go back and forth. I like to use the advantages of both. I don't have many CPUs at my disposal, so Spire and EMAN 2, I don't use as much as I'd like to, but that's just because I don't have the CPU power that they require. So don't cripple yourself by sticking to one software. Um, you can become an expert in one, and that's phenomenal. But remember that multiple packages exist because each one gives you a particular advantage that the others don't have.
There's been a lot of software developments, and there are different types of particle pickers. There's also now we move now to patch motion correction, particle polishing, Bayesian polishing. Now we can also correct for coma, and there's even tighter masks. Could you speak a little bit about on development of best practices for a single particle analysis and how much, so I'm actually combining like 4 or 5 different questions
Yeah,
together.
yeah.
Um, but perhaps a good way would be how much weight would you put in each? Because let's say you go through a workflow um, and you have 10 steps, but they're not 10 equal steps. How do you parse, should I work more on one versus the other? Because you could always keep on refining and refining, refining, but how do you know when to stop?
The when to stop question. So this question is always true. It's also true in X-ray crystallography. When you talk about R and R free, when do you stop? And you know, when I was a grad student, I used to refine and refine. And you reach a certain point where you're spending all this time, and it's just the numbers aren't improving all that much. And you start looking at your structures, and your structures aren't changing a whole lot. So you wonder, how much more should I do this? Until I read a review, and this was from a prominent individual, and they said, you refine until you're sick and tired of refining, right? So there wasn't any metric to get to, but you're supposed to be converging on something. So for example, in X-ray crystallography, if your R and R free are like at 33% and 37, you still have work to do. So there are targets to hit, but you can always continue refining, and that never stops. And there's always someone along who's going to come along and they're going to do better than you. So trying to get the optimal resolution and the optimum, the best that is possible is just not doable. I mean, a better piece of software is going to come along and it's going to do better than what you did. So the question is, what question are you trying to answer? What scientific question are you trying to answer? What resolution do you need to be to answer that question? And so best practices, and some of the techniques that you brought up, some of the refinement steps that you brought up are tiered, meaning you don't do Bayesian polishing if your 2D class averages look like crap, right? You're not going to get to that stage. You're not worried about B factors if your reconstruction looks like garbage. You're not worried about how good your 3D classes looks like if your 2D class averages look like crap. So the very first thing is, how does your 2D class averages look like? Do you see features in them? And these are questions that that'll be answered when you do the tutorial, right? At every step of the data processing routine, you're getting more and more information out. Am I seeing features in my 2D class averages, or am I seeing spikes in there? If I'm seeing spikes, I'm over refining. If I see features, do I see multiple orientations, or do I see the same orientation over and over? It looks beautiful, but that's useless because you don't have the orientations needed to get the structure that you need. And then people get stuck on Bayesian polishing. And I've seen this run on our little cluster for days on end. And it improves the resolution, but how much is it really improving it? And do you really need that improvement? So I don't mess around with this stuff, not because I don't think it's important, but because you're going to go from 3.2 angstroms to what? To 2.7 angstroms? What does that give you? Not much, right? You're not getting, the next step is a 2.2 angstrom, right? Or really it's a 1.8 because that's when you see the protons. Going from 3.2 to 1.8, that's a huge, you see protons that are much higher than that. But if you think about it, is it really worth the investment to go from a 3.2 angstrom to a 2.7? Is it worth the resources? And if the answer is yes, then you do it. If the answer is no, then you don't do it. So my luck of the draw has been, it has not been that important. Improving a 2.9 angstrom map to a 2.5. I did this again as a graduate student in X-ray crystallography. Didn't improve the story one bit. And then I was working on an enzyme, right? It didn't improve it one bit. So ultimately, I spent a lot of time going back, re-indexing, re-integrating, doing all this stuff. It wasn't worth it one bit. The story didn't change because the atoms, they move a little bit, but that doesn't tell you anything about the enzyme mechanism. You only get more insight if you start seeing protons. So that's my little spiel on that.
So basically, it sounds like if you have the right biological question or you pose that in the beginning, then the answer falls quite straightforwardly from when is enough.
Yeah. And then there are resolution gaps. For example, better than 10. At 9, you start seeing secondary structures. At 4.5, you start seeing separations between your beta strands. I think at 4, you start seeing the pitch of your helix. At 3, somewhere around 3, you start seeing side chains. Around 3.7, you start seeing side chains, and then you start seeing carbonyls. Then you start seeing protons. So these are really the landmarks you're aiming for. And going again, if you're not passing these landmarks, it becomes, excuse my language, but it becomes a pissing contest. And you're not getting any additional insight, whether you're talking about biologically or chemically. It's just, there's nothing there.
I guess this brings up another question. When you have a novel data set, maybe another way to reiterate what you're saying, what would your steps be? So let's say here's a new data set. Is this even a data set you should spend time on?
Yeah, look at your 2D class averages. Number one, are you getting good 2D class averages? If you have tiny particles, now it's hard, right? Because getting features out is am I looking at features or am I looking at noise? You can look at the background. See, is the background flat? Is it not flat? Other things you might start having to play around with. For example, if you're using Reliant, you might have to do ignore first 0, in which the background is not the nice black background that you saw before. So it becomes a little bit harder, but number one, am I seeing good 2D class averages with features? Number two, am I seeing multiple orientations? Number three, how heterogeneous does it look just by eye? And then am I getting in reasonable ab initio? Can I do 3D classification? Forget the FSC curves. Again, I've gotten 3.2 angstrom FSCs, garbage, doesn't mean anything. Am I getting reasonable maps? Reasonable is hard. It's easier to understand for a structural biologist. If you're coming from a non-structural biologist background, it becomes a little bit harder. Okay, so at 25 angstroms, this is going to be tough. At 15, it's going to be tough because everything looks blurry. Only when you start seeing secondary structures do you think that, okay, this is locked in, this is going to be done. I just need to either collect more data or maybe just keep pounding this data set a little bit more.
At one point in time, we thought particle picking was a known issue, but now it's moved beyond just picking to picking and validation concurrently, or you have a heterogeneous sample and you don't exactly know what you're picking. Best efforts, you don't mean to have a heterogeneous sample. It just, that's what happens. How has neuropickers helped? Have you ever used neuropickers, or have just standard picking been sufficient?
So if I'm working on a project that essentially I'm looking at different complexes, standard template pickers work. Nowadays, I go straight into Topaz, right? And I use Topaz's default models that it provides. So again, go through the tutorial, get an understanding of how the software works. And then what I do is the biggest factor I play around with Topaz is the binning factor, right? The models require particles of a particular size. So you can see by eye, you can measure by eye how big your particles are, and you can start binning, trying to get the particle diameter that fits the diameter of the default models that ship with Topaz. And you know, I had a data set that was not working with using regular template matching. And I decided, well, what the heck, let's give Topaz a try. Put it in Topaz, and lo and behold, I got additional orientations, and the data started working. I put it into Reliant, it wasn't working. Took the same data, cleaned up data set. Initially in Reliant gave me the good 2D class averages, I cleaned it up, but the 3D classification just was not working. Meaning that I kept getting these blurry 25 angstrom maps despite having 190,000 particles. Threw it in CryoSpark. Within 30 minutes, I got a 3.5, 3.7 angstrom map. What the hell is going on? So I cleaned it up in CryoSpark a little bit more, threw it back into Reliant, still wasn't working. So some weird thing is going on there. I don't know whether it's machine learning algorithm versus maximum likelihood, but this is an example of why you should use multiple software. But going back to Ed's question, I go to Topaz right away because I've used it enough. It fits into the CryoSpark routine. You can do it outside of the CryoSpark routine. And it's one of the better, from my understanding, it's one of the better neural learning algorithms. So give it a try, give it a try. Again, start with the tutorial, start with data that works. Don't start with your data. Don't waste your time like that.
So talking a little bit more about the workflow. So when you're trying to do refinements, how do you know if you're over refined? In 2D, you can see streaking, but let's say you're 3D, what are the hallmarks for you? Also, corollary to this, masking, how would you create masks?
Okay, so the over refinement in 3D, I haven't really had a whole lot of issues in 3D. Generally, I always have it in 2D, right? In 2D, you see the spikes. In 3D, the spikes turn into garbage, right? Your 3D reconstruction is garbage, but this is not over refining. You just have garbage. So I haven't had this problem too much. So it's, I don't know exactly what the best strategy to deal with it, but one problem I could see having is that you're getting a better resolution than you actually have, right? And this, for example, if you're seeing 2.5 angstrom resolution and you're not seeing any, you're seeing a 2.5 on an FSC and you're not seeing any side chains, you got a problem. Although I've never seen this. Once you see side chains, it's locked in. The FSC tends to be correct. With the exception of if you have preferred orientation. If you have preferred orientation, the global FSC is going to report on the highest resolution. And so you could have 4 or 5 angstrom in one dimension and 2.5 or 2 in the other dimension. So that's when you run something like 3D FSC. And this will tell you how much anisotropy you have in your data. And if you have anisotropy, and everybody has anisotropy, and you'll have to go back and you'll have to deal with that. Either throw data, most likely you're better off just tilting the stage and getting additional data. Throwing out data is not going to improve your situation all that much. It may make the map look a little bit better, but ultimately it doesn't fit the quality, the model into the map any better. So over refinement, I don't think is as much of a problem now as it used to be in the past, because now if you can get to the Holy Grail where you can see side chain, and you can also see, if you're experienced enough, you can see anisotropy in the side chain itself. It'll be elongated in one dimension versus the two. And you look at it, you go, well, this lysine in this orientation looks phenomenal, but when I turn it over, a phenylalanine can stick in there as well. Or what the heck is going on? Well, that's because you've got anisotropy in there. And you run the 3D FSC, it'll tell you. So so I think that's about all I have to say about that.
How valuable is live processing during data collection for you versus just, you're about to answer, you can continue.
So I haven't done it, but I know testimonials for people who work at national centers and who do it. I've seen it being done at NYSPC, and it's the rate at which data is being processed is so insanely fast that I can see that it's I can see how important it is. Now, having said that, you need to have software that can, and this is probably being developed, that can communicate with it. So for example, if CryoSpark at 1 a.m. says, you have plenty of data, but it's anisotropic, tilt the stage. Nobody's there to tilt the stage. What good is it? But if it says tilt the stage to another piece of software, and the data collection software says, I'm going to tilt the stage, and then you come in the morning and all of a sudden you have a 45-degree tilt, and you're like, I didn't want it, but CryoSpark or the live Relion says, do this, then that's really a huge step forward, right? Because now you have software that's intelligently collecting data, and it's not just, and this again, Legion with this rapid data collection, you're collecting like something like 3,000 micrographs a day, which is an insane amount of micrographs. You really don't need that much, but this is the first big step forward into making things like this happen. So I see CryoSpark Live has made a huge impact for some individuals. Again, I haven't used it, but I can see that software like this is going to even make more of an impact when it's supplemented with some of this additional software that's being developed. It's probably being developed, I don't know.
At most national centers, you can collect anywhere between 2,000 to 10,000 images a day, depending on your settings and grid. I mean, you need a really good grid, but that speaks to what is a minimal data set for you? Are you going by micrographs, asymmetric units? Because when you're beginning, that's very hard to decide. Once you have some data, then you can maybe do a B factor plot and say like, oh, okay, this is reasonable. Okay. But when you're starting a novel project, what would be a good goal?
I would say probably 3,000. One day of data collection is more than enough to know, is well more than enough. If you can collect 300 micrographs, I would say that's more than enough as well. I wouldn't talk about asymmetric units or anything like that, because you should be able to get if you can't get a reconstruction out of that few particles, or if you can't see good 2D class averages in different orientations, I think then you got to work out more on maybe on the biochemistry, or maybe on maybe you're having preferred particle orientation. But I don't think you need a tremendous amount of data. Sometimes just screening, if you're screening and you see good ice and you can see particles in the ice, and you have a FEG, meaning either a Arctica, glacios, or something like that, or something higher, then go ahead and collect a 300 to 500 micrographs to see with particles in them, and see it's probably maybe 10,000 particles is a reasonable start to go ahead and see if it's worthwhile pursuing, or if you need to make modifications.
I'm going to shift the discussion to sample prep. There was a question regarding your lecture about the different models of sample prep devices. Could you comment more about what you believe is the most common, I guess, plunge freezing device, and what's your go-to plunge freezer?
So I don't do plunge freezing anymore, but probably the most common one is the Mark IV, because you're buying a microscope from FEI and they're going to throw in a plunge freezer for you. So why not buy it, right? Or why not get it? So that's probably the most common one. Other ones before the Mark II, I think there was a Mark III and a Mark II. The difference is with Mark IV, you get pressure. You have some additional options you can play around with. There's the Gatan CP3. There is the Leica has one as well. Each one gives you some additional options to play around with. And then there's some groups that go with the good old gravity-driven plunge freezer, which is you have this contraption that somebody made in the metal shop. You put it in a cold room, you turn on the tea kettle, humidity is coming out, and then you start freezing grids like that. And these labs, this takes a lot of practice, but the labs that do this swear that the ice coming out of that are just leaps and bounds better than what you can get out of a Mark IV. And they exclusively use that technique for their work. And these are labs that are putting out structure after structure after structure. It's not like, oh, this is one structure we get out in a very long time and it just takes us forever. But no, these are extremely efficient labs, and they swear by this technique. So if you have the time and if you have the motivation, it's something to pick up.
A lot of sample preparation seems to be empirical. Do you have samples that you've worked on that you're surprised by the conditions you eventually needed to get a good grid?
No, so I have not done that. So we make our own samples, and so a lot of time is spent on making the sample, and not so much time is spent on trying different types of conditions. One of the reasons why I don't pursue this strategy is because ultimately there's no way of screening through grids in an efficient manner with Cryo-EM. So with crystallography, you can screen through 1,000 conditions. Why? Because you have a light microscope that takes an image. Do I have a crystal or not? Who takes the image? A robot does. Who says that there's a crystal or not? A robot does. But you can sit in one afternoon and look at 1,000 images and say, I see crystals in these images, and let's go forward. There's really no such thing for Cryo-EM, right? Some people tried this for 2D crystallography, and this was done at NYSPC. But again, you couldn't go through 1,000 conditions because ultimately it's got to go into an electron microscope, and an electron microscope has many more pieces than a light microscope has, and it has a lot more opportunities for something going wrong. So because of that, I haven't spent a lot of time on playing around with this thing. And you read manuscripts where they say, we did these things and we found this additive made a huge difference, and this is why the additive works. And everything is scientifically sound, but when other people use it, they go, well, this didn't work for me. How do you say this is valid? And the reason is, like in crystallography, we know when they first started out, they had a few conditions. And then they quickly learned that that's not how you get crystals. If you want crystals, you run a screen and you find as many things as you can find, and you throw that inside of the screen and you make 1,000 conditions, 10,000 conditions, try 30 different temperatures and try as many things as you can until you find the thing that works. So you went from this intelligent way of doing it to high throughput, and high throughput always beats intelligence because there's more unknowns than there's knowns. And I just can't come up with a way of coming up with a screening methodology that works with Cryo-EM.
So you put more emphasis on generation of the sample biochemistry, molecular biology. Have there been any targets that, okay, you spent best efforts, you spent 100 equivalents of people time, like let's say if you have 100 people working 1 year, it's like 100 years on this construct and you can't do any more and you must push forward. Are there any tips and tricks that you would try?
Well, so antibodies, get fabs against your complex. Fabs are 45 kilodalton. Fabs have a very unique structure, easy to see with EM. If you can raise antibodies, monoclonals against these things, There are individuals, there are labs who generate antibodies against these things. There's technology out there. You can try nanobodies. I would say if you really have to get the structure and you have the support for getting these and you've tried everything, look into this technology. Some labs, they work with small membrane proteins, 90 kilodalton. They don't even bother doing anything else. Right off the bat, they have a collaboration set up and they say, we have these 4 fabs against my complex. We tried all 4. This one worked. It gave us the structure. Okay, so that's still screening, but you're screening biochemically. So that's what I would say. If everything, first thing I would do, but you know, guys, this stuff is not cheap either in terms of cost, nor is it cheap in terms of time, because making these fabs it takes some time. And you don't want to say, I tried freezing my grid, I tried 2 grids, it didn't work, give me a fab. That's not the way to do it. But once you've done everything, really that's the first thing I would look at.
I think we hit most of the main questions. I'll ask a couple more to give students, if you have additional questions, just put it in chat or raise your hand and you can pose that. But Reza, how accessible do you feel Cryo-EM really is? How broadly applicable would it be? Would any structural biologist, would any researcher in biology be able to use Cryo-EM as it is today? Or are there certain areas that we still need a lot of development in?
Okay, so one thing I forgot one point I forgot about earlier question about the different freezing methods. Spotted on, which is now chameleon, is also another thing to try. Okay, once you've tried everything, spotted on was developed at Scripps and at NYSPC. This thing works like a charm. It gives you outstanding ice. There have been situations where it has worked. We tried it once. We have a bad sample. It didn't work, but you know what? Give this thing a try as well. It's everything works. So having said that, how accessible is Cryo-EM? Unfortunately for me, it's too accessible. I'm losing collaborators because they're like, well, why should I work with you? I'll go do it myself. But that's what's phenomenal about the people who have worked in Cryo-EM, right? You know, I've heard about the stories when EM was starting out with all the bad press not bad press, but the bad attitude that Joachim Frank was getting, that, oh, why are you working with this nonsense? This is blobology. And, you know, at the end of it, he proved all of them wrong. And he proved that this is a beautiful technique and it's revolutionized not just structural biology, but just biochemistry, just science to begin with. So it's extremely accessible. And again, I ragged on one technique earlier on. I'm not going to bring it up, but it's not one that I'm fond of. And it's just because it's not accessible. And I think it's not accessible for the other technique because I think the researchers have intentionally made it not accessible. I don't think it's because the technique is hard, but I think it's just been intentionally driven that way. And EM, for whatever reason, ever since I started, has been a very open community. It was far more open than X-ray crystallography was. I mean, we had these NRAM meetings where almost everybody that was doing EM would get together and share all these ideas. And I'm like, I've never experienced anything like this before in my life. Why is it like this? And it's maintained that state. And everybody wants to share. Everybody wants to tell one another what's happening, how to improve things. And that's really unique in this field as far as any experience I've had. And anybody can get in, anybody can do it. National centers are popping up, one being at NYSPC. And I think these things are going to get better and it's just going to keep getting better and better. And I mean, I've spoken to folks at FBI and they want to make this into a turnkey operation. They want to make it like a absorption spectra. You put the sample in, you push a button, you get your reading. You don't know the physics behind it. There's a lot of physics that go behind absorption spectra. Nobody knows. I mean, I don't know it, right? I don't think many people in this Zoom session know it, but they use it on a regular basis. SDS phage, there's a lot going in. Nobody knows how to use it, but it's probably the most used technique in biology. So, so that's what they want to make EM, and people that make the software development also want to do that. So that's the beauty of this field is that you're getting more and more people getting into it.
We have a couple last minute questions. When you're making grids, do you have a particular ice thickness you're aiming for? And along with that, have you ever tried detergents to try to manipulate the ice thickness?
So I have not tried detergents. So ice thickness, you know, I try to go something the size of the particle, try to get it as thin as possible without losing the particle and without getting particle orientation. Because I have one particular particle that's thin in one dimension and long in the other dimension, and we keep getting preferred particle orientation. We've tried packing it in by using a high concentration, but then it becomes so packed in that again, you see the top orientation. I think the side orientation, I think is just so small that it's not working out. So I would look at I would collect the data and I would process data based on ice thickness. Because when you have a grid, you're going to have ice thickness all over the board. Not all over, well, at some points it's all over the board where you have no ice and you have absolutely thick ice where the beam doesn't penetrate. But you have, there's a variance there. And I would say, try to bin the data into different particle thicknesses, extract particles from there and see which one gives you better looking class averages and multiple orientations. And sometimes the thinnest one gives you the better particle orientations, and you might have to tilt the stage. But it's one of those things where I would collect a little bit of data and get a feel of what I'm looking at. Don't try to say I need to shoot for 70 nanometer ice thickness, or I need to shoot for 20 nanometer ice thickness. And if it's not that, then it's not worth data collection. So you need to do something to know where to start. You got to start from somewhere. This is what I'm saying.
And the final question, you can actually look in the chat yourself. Maybe you can repeat the
Sure.
question, and that way you won't have the game of telephone, me paraphrasing.
Okay, so in data processing, what are key statistical parameters to look for to assess data quality, other than quality of 2D projections, resolution, and the map? So this comes from Suzanne, who's actually an X-ray crystallographer. And like I said, you have some statistics, like say like in X-ray crystallography. And in X-ray crystallography, you need to look at all of these statistics to really assess it. But ultimately, it's the R and the R free, and it's the completeness of the data, right? And the high resolution terms, a high resolution beam in X-ray crystallography, and the same exact thing fits in EM. Your completeness of the data, your 3D FSC, your resolution. That I would say is once you have a map and once you trust your map, then that's probably the next big thing you need to look at. Do I have anisotropy present or not? Then additional statistics. So there's a couple things you can do. For example, you look at your FSC curve. How does it fall off? Is the fall off sharp, or does it go like this and you have a couple of peaks, and what could those additional multiple or bimodal, somewhat bimodal distribution mean? So they could mean a couple of things, but statistical parameters to look at the actual data. You know what? One of the problems with these parameters is that a lot of times they look for consistency, right? So you're looking for high precision. You're not looking for high accuracy. And you need to step away from the precision and start looking at accuracy. And what really looks at accuracy in crystallography is your R free, right? You can have data where everything looks beautiful, but if the model you built into it is garbage, then it's really not that good. And even if you have phases coming from SAD or MAD or SIR or MIR or something like that. So for key parameters, you can also look at the quality of the map. You can calculate FSCs between your Cryo-EM map and your fitted model. That's giving you something getting close to the R free or FSC. You can try maybe things like maybe FSC free, although I haven't, where you set aside half the data, you refine against half the data, and then you calculate an FSC against the second half of the data. So essentially your atomic coordinates do not see half of the data. And you could use that as an FSC free kind of metric. So those are the things that I can think of key statistical parameters. But ultimately, if you're coming from a structural biology background, does the resolution number make sense, right? Are you seeing side chains when you're supposed to see side chains? Are you seeing separation between your beta strands when you're supposed to? Are you seeing carbonyls? Things like that.
Okay, so that's it for the question. So unless you want to get into an FSC conversation, maybe have some last words and we can wrap up.
No, I don't want to get into an FSC conversation. I can ask questions. I mean, there was one question that was put up about, you mentioned binning particles into 64 by 64, and then the binning question, why do I think 64 by 64 is something that should be done? And the reason is that, look, the computer aligns pixels to pixels. It doesn't care about resolution. It doesn't care about pixel size. In my experience, 64 by 64, assuming you don't have a tiny particle inside of a huge box, assuming you did the 3x and no bigger than the 3x, 64 by 64 has historically worked really well for me. It expedites the entire process. You lose resolution information, but you don't care about that. You want to clean up the particles. Once you have clean particles, and you can even do your 3D classification on this, once you have clean particles, extract, unbind, and start processing the unbind data. So you're not losing any resolution at all. You're just expediting the entire process. Um, and that's why you go to 64 by 64, just to expedite it. And then there was a question of, what does it mean by binning? Binning, I guess, in the traditional ways of binning was averaging two neighboring particles, but then we start doing Fourier transform binning, and that's essentially sampling at different frequencies. So for example, you can bin in audio, you can bin in video. What do I mean by binning? 44 kilohertz in MP3, 22, 12. This is some form of binning. In EM, you have your pixel size. You can go from 0.5 to 1. I guess if you have an instrument that can measure smell, there's a way of binning that as well. So it's essentially sampling at different intervals. That's really what binning crudely means, without getting into all the jargon. And how much you bin depends on the size of your particle. If you have small particles, you don't want to bin too much. And if you have large particles, you have a very small pixel size, then you're going to have computational problems. You're going to start running out of memory. You're going to have to be a little bit more creative with how you process your data. So anything else?
I think that covers most of everything we wanted to cover. Do you have any
Great.
last words for our students? Otherwise, we can wrap it up.
Yeah, so I guess I've said everything I've wanted to say. Um, my recommendations are, again, what I've said. Use every piece of software at your disposal. You guys have a huge advantage here that these courses are going on and they're available online. We had the NRAM courses, which were done once every other year. I don't know if they're still being done, but these are phenomenal. I learned a tremendous amount there. But these online things are extremely useful. Again, you guys should be grateful for NYSPC for making this available. And you know what? Play with the software. Don't be afraid of it. Don't be afraid of the command line interface. It's what makes you distinct from other scientists, right? You're a little more geeky, you're a little bit more nerdy, but that's the beauty of having computers at your disposal. Don't be afraid of it. And if you are afraid of it, well, there's things like CryoSpark, but yeah, that's about all I have to say.
Okay, well, thank you so much for joining us, Reza.
Thank
And
you.
for the students, don't forget Wednesday is Journal Club.
All right, thank you guys
So
and women, ladies.